going to be learning about heaps. This is my personal study, but you get a chance to learn with me. So it says, let's go over the heap pattern. It's a real world and it's real world examples. So imagine you're at a busy airport. Flights are constantly landing and taking off. You need to quickly find the most important flights. So let's say an emergency landing or a VIP departure. At the same time, new flights must be integrated into the schedule. How do you track all these while finding the highest priority flight quickly? So we have different flights, and we want to ensure that we get to our destination quickly. We want to get the highest priority of the flight. So without an efficient data structure, we can scan the entire schedule every time a decision is needed. So which can be a slow and error prone as the number of flights grows. The time complexity of this inefficient system will be O(n) because we have to check each individual flight and compare it. Where n is the number of flights because it requires scanning the entire schedule to find the highest priority flight. So this solution is heaps. Right? Heaps are a special data structure that helps you efficiently manage priorities. So what heaps does is that it helps you to select based on priority. So with a min heap, you can find the flights with the earliest priority, and with a max heap, you can focus on the flights that have been waiting for the longest, all while making updates quickly. So, the min heap enables you to find the earliest flights. Max heap enables you to focus on the flights which have been waiting for the longest, so they are not the earliest, right? I believe maybe the latest, but as I read we'll keep on going. You'll learn more. All while making updates. So a heap is a specialized binary tree which satisfies the heap property. So if you remember what trees are, right? Trees are their data structures. So you can have branches in a tree. So the mean heap, right? I'll draw it for you inside this video. I will insert a picture of it. So the mean heap, the value of each node is smaller than or equal to the values of its children. So the root node holds the minimum value. A mean heap always prioritizes the minimum value, while a max heap prioritizes the maximum value. So it holds the maximum value. So the node is usually greater than or equal to the values of its children. Well, a priority queue is different in this sense, right? It allows you to customize the priority. So let's say you don't want min or max. Let's say you have another where you want to customize how important the value should be placed, right? You want to make it special, right? The priority queue can help with that. So it helps you retrieve elements based on custom priorities. And so it is used for heap efficiency. So, what is a heap? Right? A heap is a specific data structure with fixed ordering. So, when we say fixed ordering, either min or max. While a queue is an abstract data that helps handle custom priority requirements. So, let's look at what heaps are usually used for. Right? So, heaps are implemented to efficiently access parent and child nodes. So, like we mentioned before in that flight scenario, let's say that we want to find the earliest departing flight. We can easily do that using a heap, I believe a min heap, because we can find the earliest ones using the minimum values. Now, there are three major operations performed in heaps. So there's the add operation, which helps to insert a new element into the heap, and this operation takes O log n time. There's the delete operation, which removes the root element and rebalances the heap, which also takes O log n time. And there's the peak. So what the peak does is that it helps you retrieve the smallest or the largest element. Now, let's look at this demonstration over here, how we can build a min heap or a max heap and how they can be used to solve several tasks. So remember I said I would insert how we could solve this. So let's look at it together. So we'll first construct a min heap from the array below. So we have 10, 11, 3, 7, 2. When constructing a min heap, remember the node is the least value. So let's look at it together. So 10 is inserted into the heap as the root. Now, when we have 11, remember the node has to be less than the value of its children. The parent has to be less than the value of its children. So we see that 10 now is attached to 11. Then we now have 3, right? 10 is attached to 3. Why? Because the node has to be less than the value of the parent node has to be less than the value of the children. So when we have 7, we'll put 7 above 11, right? And then 2 will be the highest node, the highest parent node, the head node, right? This is because, like I mentioned before, I'll repeat it again for us to remember, right? The shortest or the least value is always going to be the head node, right? It's always going to be the parent node at the top, and that's just how min heaps are. So we can now construct a max heap from the same array too. So let's say that we have 10, 11, 3. We still go about it a similar way. We put 10 first, but this time 11 is going to be at a higher node value, right? At a parent node value than 10. So let's continue. Then we append 3, we add 3 to this heap. Then 7 is going to be after 10 because the parent node has to be greater. Then we have 2. So this is an example. So can we see the difference between the min heap and the max heap? So all of this was created based on the array that was provided for us. But the min heap, the highest node, right? So the parent node, let's see what it's called here. The value of each node is smaller than or equal to the values of its children. So 2 is smaller than 3, 2 is smaller than 10. But when we look at 11, 11 is greater than 10, 11 is greater than 3. So we see that the values are increasing in the min heap and the values are decreasing in the max heap. Now let's look at some popular problems that we can solve. Heaps are powerful because they allow us to maintain order. So let's say minimum, maximum without needing full sorting. So in that scenario now, I didn't have to sort the algorithm. If I was sorting the algorithm, it might take a longer time. So they're also used when we need to repeatedly access the smallest or largest elements in a data set. So let's look at a problem like the last stone weight. Okay, in this problem, we are given an array of stone weights tagged repeatedly, with repeatedly smashing two heavier stones together. If the two heavier stones have the same weight, both are destroyed. If they have if they have different weights, the smaller stone is destroyed, and the smaller stone's weight reduces the larger stone's weight. This process continues. So to solve this problem, we need to repeatedly select the heaviest two stones so that when we smash them together and update the list of stones based on the results of each smash. So if you want to receive the largest stones, right, we can use a max heap because the max heap it calculates the maximum. So using a max heap will allow us to easily access and remove the heaviest stones while ensuring that the heap structure maintains its property, the property of providing the largest element at the top. So to begin, we first place a max heap using the stone weights. At each turn, we pop the two largest stones from the heap. If the two stones have the same weight, both are destroyed. If the two stones have the same weight, both are destroyed, and no stone is added back to the heap, right? So we're just looking at it here. So this is just a way to solve the problem, right? If they have different weights, the stone of the smaller weight is destroyed, and the one of the larger weight is reduced by the stone's small weight and pushed back into the heap. So we're basically using the heap to calculate the highest values, and then if two stones now have the same weights, we're going to destroy both of them. But if they have different weights, the one with a smaller weight is destroyed, right? And then the one with a larger weight is reduced by the smaller weight stone. So this process continues until no stone remains or stands. And the time complexity of a heap-based solution is O n log n, where n is the number of stones. This is because building a heap, because you have to pass through each and every of the values, it takes O of n time. And then each of the n smash operations involves heap insertion and deletion, which takes O log n time. So in contrast, the naive solution, which would be to scan the entire list, find the two largest stones. So if we want to do the brute force approach, we would scan the entire list of stones and then we'll be checking for the one which is highest, the one which is lowest. And in a situation like that, it will give us a time complexity of O of n squared due to the need for n scans of O of n each. So in this solution, we can use two heaps, and I'll show some more examples. You can see that they are very detailed. They're very detailed in the explanation on educated.io. I believe educated.io has really helped me to understand how things work. So I encourage you to get your own subscription. So given this array, the task is to find the medium of all windows of size 4. So these are some examples of some things that we can use to solve some problems we can solve with heaps, right? So it's saying that we have a window size of k. Right, we want to get the medium of each sliding window of size k as it moves from left to right. So let's look at how this problem will be solved. This problem is called sliding window of median. So we have a small list. So we have 1 and we have -1, and we have a large list which is 2 and 3. So the median here, right, which we just get the first top note, is 1.5. Let's continue. 1 and 3. So the median here is 2.0. Now let's continue. The median here is 1 minus 1 plus 3 minus 2 divided by 2. That is 1. Minus 1 plus 3 plus 2 actually. So guess what we're doing? In a min heap, right, the value of the parent node is greater than the value of the child node. But in a min heap, sorry, I don't want to confuse you. In a min heap, the value of the parent node is greater than the value of the child node. In a max heap, the value of the parent node is less than or equal to the value of the child node. So when we want to calculate the median, we just need to get the top parent node and then add it together and divide it by 2, which is what we are currently doing. So you see that it keeps on changing. We're using the topmost value. Okay, so we see how the heap really simplifies the solution for us. Now, another question that we could solve with this is, given a continuous stream of numbers, find the medium of the numbers seen so far after any intersection in constant time. So it says the idea is to maintain two heaps, min heap and max heap, to keep track of the numbers seen so far. The top element of both heaps will aid us to find the median at any point in time. So we have our input, our min and max heap. And what we're trying to do is we're trying to find the median of the numbers, right, of a number stream. So the first number is 22. So we just push it to the max heap. Now let's continue. The next number is 35. 35 is larger than 22. So we push it as the head of the min heap. Now, the median of these two values is 28.5. So if we say 35 plus 22 divided by 2, so we still have more values because 30 is pushed in. 30 is less than 35. So we replace it and make it the top parent value. Let me calculate what I just said just to ensure that I'm being accurate. So 35 plus 22, 57 divided by 2. 7 divided by 2. So it's 28.5. So we can keep going. So our max heap, right, we insert 13 because 13 is less than 22. So something to always remember, min heap, the value of the parent node is greater than the value of the child node. The value of the node is greater than the value of the child node. Max heap, the value of the node, the topmost node, is less than the values of the child's node. So it's something to keep on remembering because it will help you not make the mistake and not switch it, right? So I have a question. Let's say that you have a question given to you in an interview. How will you know that, oh, the solution to this problem is a heap problem? Like, well, how do you tell? So these are some conditions that you might want to look at. So for example, the linear data. So if the data is linear, it can be sorted or unsorted. A heap will efficiently find the maximum or minimum elements there, right? So operations like insertion, delete, this ensures fast access to the top. If the data is already sorted, a heap can be useful when frequent intersections and deletions are required. So let's say that we want to keep deleting values or we want to keep adding values, right? A heap can really help us do this because it allows us to update it efficiently, and allows us to update it efficiently, right? Either we want to insert or delete, and this process just takes one log n time. Now we can also use it for streams of data. So when the input data arrives on time consistently in an unpredictable order, we can use heaps, right? We can use heaps to enforce priority ordering. So let's say that we want the largest weight, the smallest cost, the highest frequency. This saves you from manually resorting or scanning each time your data changes, which helps to save time. Right, and if you want to calculate maxima and minima, remember, min heap can help you calculate the minimum, max heap can help you calculate the maximum. So if you're given a string of consistent data, right, and you want to calculate the maximum or the minimum of it, a heap is very useful. Efficient retrieval of extreme values. These are some reasons. Custom priority based selection. So something places where heaps are used. We have video platforms, right? Video platforms. Let's say that we want to get the medium age of viewers on a video platform. We can implement a functionality whereby the median age can be updated effectively when a new user signs up. Because the good thing about a heap is that you know where the least value will be positioned, you know where the highest value will be positioned. So you can easily use a heap to calculate this, and then you can use it for game matching too, right? So if you want to match players of similar skill sets, right, to enjoy a good gaming experience, you can use heaps to do that too. Thank you so much for watching. The next video we're going to be on this playlist, on heap playlist, we're going to be talking about practical questions that you can solve on LeetCode to improve your understanding. I'm also learning to if you have any comments or any questions, you can put it in the comment section. Thank you so much.